Okay, we are back with sections 5.3 and 4. We're still looking at power, shear stress with torsion, angle of twist, and this is our example number 2. So we have a solid circular steel shaft having an outside diameter of 35 millimeters is subjected to a pure torque of, the shear modulus is given as, determine the maximum shear stress. So if we're dealing with torsion, that's going to be TC over J for maximum. And figure out our angle of twist, and that's going to be phi equals TL over JG. So before we get started, I'm going to make sure I know which equations go with which part. So I went ahead and I drew, it's a solid circular steel shaft, so I have that solid shaft drawn. I know that the maximum occurs at that outside fiber. And so I went ahead and drew C. I know that my inner radius, or it doesn't matter if it's inner because it's not it's not hollow. So our radius is diameter over 2, and because it's solid, our polar moment of inertia is pi over 2 c to the fourth. So let's get started on this. I also, when I see gigapascals or anything that's not in newtons and meters, which is what I'm comfortable with, then I'm going to go ahead and write this as 80 times 10 to the 9th, and I know a pascal is a newton per meter squared. And that way I can be like newton meter, newton meter, newton meter. I just need to take care of my diameter. So shear stress equals TC over J. Our torque is given as 640 newton meters. C is our radius, and so it is going to be 35 divided by 2, which is, I think, 17.5. Yep, 17.5, but that's in millimeters, so we're going to have to get this into meters, divided by pi over 2, and again, my radius is 17.5. That's in millimeters. I need to get it in meters to the fourth. So as we're working through here, we have 640 newton meters, 17.5 enter, 1,000 divided by, times, and then we have pi over 2, 17.5 enter, 1,000 divided by, and then we're going to take that to the fourth, times, and divided by. And I get this very, very long number. So when I count over, I have to remember this is in newton meters. Okay, so it's really long, 7602316.5 newton meters. So 1, 2, 3 kilo, 1, 2, 3 mega. So this is going to be 76 mega, and stress is in newton per meter squared. I was like, wait a minute, that's not working out right. Newton per meter squared. So I'm going to have 76 times 10 to the 6th, which is mega Newton per meter squared Pascal. So that's what my shear stress is, 76 megapascal, and that occurs at the outside edge. So if we wanted to sketch this, if I wanted to go back and sketch it, I don't know which way it's twisting, but we'll just assume this way. So I could go back and sketch it, and I know that it's linear, and the maximum is occurring out here at the outer. So there would be that. Now we want to determine the magnitude of the angle of twist and a 1.5 meter length of shaft. So our angle of twist is TL over JG, and we're going to just set up the same way. So I have 640 Newton meters. I have a length of 1.5 meters. I have J, which is pi over 2, and then I've got 17.5 millimeters divided by 1,000, all of that to the fourth, and 80 times 10 to the 9th Newton per meter squared. So everything is in Newton meters, 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 Newton per meter squared, and everything, this should all come out. Those go away, meters squared, this is going to go top, meters squared to meters fourth over meters fourth becomes unitless, which is my angle of twist in radians. So let's get started there. So we have 640, 1.5 times pi as a number, 2 divided by. Okay, 17.5, 1,000 divided by, to the fourth, times, and then 80 e to the 9th, times, and then divided by. So we get this very tiny number, 0.0814 radians. So our angle of twist is 0.0814 radians. And if well, what is that in degrees? Who knows? We can always go back to that. We have that circle where we have 1 revolution is the same thing as 2 pi is the same thing as 360 degrees. And so when I'm looking at radians, I can always multiply by 360 over 2 pi to get it into degrees. So we're going to have an answer. We'll get that in just a minute. So we have 360 times 2 divided by pi as a number divided by, and I get 4.67 degrees. Okay, so my phi is actually in radians, 0.0814 radians, but I also found that that was 4.67 degrees, because in my little brain, it's just easier for me to understand degrees than radians. So there's our answer.